everyone, my name is Jocelyne Laflamme. I work for the University of British Columbia, and today I'm going to be talking about my research simulating landscape level impacts of aspen on fire dynamics in British Columbia's South Okanagan. As many of you already know, extreme fire behavior is becoming more frequent across Western North America as a result of both climate change and historical forest management. Historically, lightning and cultural ignitions created patchy mosaics of different forest and non-forest structures, which maintained landscape resilience to fire. However, a century of fire suppression has led to the buildup of fuels and forest encroachment across much of the landscape. Forest practitioners and policymakers are starting to acknowledge that large landscape-level changes will be necessary to mitigate this new era of fire behavior. And while fuel treatments such as prescribed burning and thinning can be used to restore these landscape structures, they can be costly and difficult to implement at the scale required. Increasing the prevalence of hardwoods such as aspen has also been proposed as a fire mitigation tool, but has received little attention relative to fuel management treatments. Trembling aspen is the most widespread tree species across North America. However, rather than being promoted as a fire mitigation tool, it is often actively suppressed by forest management through manual cutting and the use of herbicides in favor of more commercially valuable conifer species. The prevalence of aspen may also be reduced due to fire suppression policies, as it is an early successional species in many regions and dependent on disturbance to be maintained across the landscape. There's plenty of anecdotal evidence that aspen-dominated stands can slow or stop the spread of fire. A recent literature review shows that these claims are also backed by research. The study found that pure aspen stands decreased fire occurrence, behavior, and severity under most conditions. Exceptions included under extreme fire weather conditions, certain seasons, and topographies. There are several characteristics that lead to aspen's low flammability, including low crown fire potential caused by high canopy base height, low canopy bulk density, and high foliar moisture content, and compact litter, as well as high moisture content in litter, duff, and soil layers. However, these studies mostly focus on the stand level impacts of aspen. Aspen's role in the landscape ecology of fire remains poorly understood. The objectives of this research were to investigate how much aspen may have occurred across the landscape under an active fire regime and how that influenced fire behavior. Because aspen forests can act as a barrier to fire spread similar to non-forest regions, we also wanted to determine whether allowing aspen on the landscape would increase forest stocking and carbon storage in resilient landscapes relative to a conifer-only scenario. And finally, we were curious how fire suppression would have influenced the prevalence of aspen and in turn fire behavior. We used simulation modeling to investigate our research questions. Specifically, we used reburn, a vegetation succession and fire dynamics model that pairs state transition models with a fire spread model. The state transition models, or STMs, describe vegetation and fuel succession for each forest type in relation to disturbance history. Each pixel is assigned a state from one of the STMs, and each forest type has a unique STM to represent different growth rates and fire responses of various species. Each year in the simulation, the STMs are used to grow the forest, and then the fire season is modeled in FS Pro using historical climate and ignition data. This process is repeated for each year in the simulation, and we typically run the model for 3,000 years to account for rare interactions between landscape structure and weather. We chose a study region in British Columbia's South Interior, which covers both cold and mixed conifer forest types. While less than 1% of the study region is currently dominated by aspen, the region is heavily managed for commercial timber, so the growth of more valuable species such as lodgepole pine and Douglas fir have likely been prioritized over the past century. We mapped forest types for conifer-only forests and then aspen-capable regions based on tree suitability ratings created by provincial ecologists and topoedaphic settings. We created state transition models that incorporated aspen and the interactions between fire history and species composition. So to clarify, the aspen-capable regions on the map are not always aspen-dominated. They are colonized by aspen after high-severity fire, and then shift to mixed and then conifer-dominated forests through succession. We ran a total of 4 modeling scenarios: altering species composition, so either conifer-only or aspen-capable, and then the fire regime, so either having an active fire regime or fire suppression. Suppression was simulated by preventing ignitions from starting fires, except for under extreme fire weather conditions. About 98% of ignitions were suppressed, which matches real-life suppression rates in the area. Now I'm going to discuss some of the results we found to date, but I wanted to preface this by mentioning that these results are preliminary and the analysis is ongoing. When we compared results from conifer-only and aspen-capable runs under an active fire regime, we found that the aspen-capable scenarios had about 26% of the landscape dominated by aspen. And aspen was more prominent in cold conifer forests than in mixed conifer forests. Average fire size decreased by 30% in the aspen-capable scenarios. And while mean annual area burned did not differ significantly, it was 20% lower in the aspen-capable scenario. When we looked at forest stocking across the landscape, it did increase by 9% in the aspen-capable scenario. However, when we looked at each forest type individually, we found that aspen increased forest stocking in the cold conifer forests, but not in the mixed conifer forests. Fire suppression drastically reduced the prevalence of aspen-dominated stands from 26% to only 5%. Fire suppression influenced fire behavior in both the conifer-only and aspen-capable scenarios. Average fire size increased by 10 and 14-fold for conifer-only and aspen-capable scenarios, respectively. Mean annual area burned was actually lower in the fire suppression scenarios because there were many years where fire suppression was effective. However, you can see from the graph on the right that when fire did occur under the suppression scenario, burned area was 2.5 to 3 times higher than that under the active fire regime. So just to summarize our results, the modeling scenario suggests that aspen likely dominated quite a substantial portion of the landscape prior to fire suppression. It also played a key role in mitigating fire size. Using aspen for fire mitigation may support additional forest cover and carbon storage in cold conifer forests, but this is not the case in mixed conifer forests. Our modeling scenarios so far have focused on historical climate, and even though they demonstrate that aspen likely contributed to wildfire resilience in the past, it's unclear whether this will hold true under more extreme fire weather conditions. Climate change will drastically shift the feasible growing range of many species, so aspen may not be a plausible tool for fire mitigation under future conditions. To answer this question, we're currently working on integrating climate change into future modeling scenarios, including both future weather conditions as well as predicted shifts to species ranges. Finally, I'd like to thank the Pacific Institute for Climate Solutions for funding this research under the Wildfire and Carbon Project. Thank you for listening, and feel free to reach out to my email if you have any comments or questions.